Are you ready for more? The image shows segment AB in several points. Calculate the distance from each point to the endpoints of segment AB. So we have to find the distance from point G to point AB, C to point AB, E to point AB, F to point AB. All right, so to do this, we're gonna do the same thing we did before. We are gonna make some right triangles. So let's start with F. If I'm looking from F to B, I wanna make one side like that, so I have an easy change in X and change in Y. So my change in X here is 3, my change in Y is 4. From F to A, that's a lot easier. 1, 2, 3, 4, 5. So F to A is only 5 units. That one was pretty easy because they're both on the same horizontal line. This one's gonna be a little bit trickier. 3, 4, and I gotta find this missing side. That's my hypotenuse. Or really, we call that C in the Pythagorean theorem. All right, well, if you remember, 3, 4 are part of a Pythagorean triplet where I know that my hypotenuse is going to be 5, right? 3 squared is 9, plus 16, and 25 equals 25. So I know that this side here is going to be 5. So that's interesting. They're actually both the same distance, 5 and 5. All right, let's see if that holds true for every single one. E going up 2 over 4. So 2, 4. E to A, down 2, back 4. So already I can see that these are going to be the same. So I'm only going to have to do it once, which is sort of nice. Let's do it for E up here. We get 2 squared plus 4 squared equals C squared. 4 plus 16 equals C squared. 20 equals C squared. And then we get radical 20 equals C. This is really not simplest radical form. You could leave it as radical 20. I'll just put it in simplest radical form, just to make it a little bit nicer. So radical 20 has 20 is a perfect square factor of 4. So I'm going to rewrite this as radical 4 times radical 5, since 4 times 5 is 20. And then radical 4 is just 2. So I can just write this as 2 radical 5. All right, so that would be for E. So 2 radical 5, 2 radical 5. All right, so again, we get the same length, obviously, because we've got the same two congruent right triangles here. All right, let's see C. So if I'm going from C to A, that's over 2, down 1, 2, 3, 4, 5, 6. 2 and 6. And then I would imagine it's the same from C to B. 1, 2, 3, 4, 5, 6. 1, 2. So those are also going to be two congruent right triangles by hypotenuse leg, right? Or I guess we'll find the hypotenuse. Yeah, what would this be? Oh, side angle side, right? Because we know this is a right angle, this is a right angle, 2 and 6. So they're congruent by side angle side. All right, so for C, we've got 2 squared plus 6 squared equals C squared. I'm just going through this quickly because it's sort of monotonous, doing the same thing over and over again. All right, this would not really be something you'd find on a test, but we'll see. Maybe it's interesting. All right, take a radical of both sides, and we get radical 40 is equal to C. All right, and just some review on how to put something in simplest radical form. I'm looking for perfect square factors of 40, so I know that 4 is a perfect square, and as a 10 times 4 is 40. Radical 4 is just the same as 2, so we get 2 radical 10 is C. All right, point G, lastly. All right, so G I can see is just over 1. This would be down 8. This is getting a little cluttered. Maybe I'll do dashed lines instead. And I assume it's going to be the same to get to B. Well, it's actually not. Okay. G is 1, 2, 3, 4, 5, 6, 7 over. And down 1, 2, 3, 4. Now let's see if those are the same. I imagine they are. All right, so for G, one of them is going to be 8 squared plus 1 squared equals T squared. And the other one is going to be 7 squared plus 4 squared equals C squared. So 7 squared is 49, 4 squared is 16. And we get 49 plus 16 is equal to 65. Radical 65 equals C. 65 has no perfect square factor, so I gotta leave as radical 65. 8 squared is 64, 1 is squared is 1, and again we get radical 65 as our final answer. All right, so we notice that all these points, which actually happen to also be collinear, meaning they're all in the same line, are all the same distance from these endpoints. So what does that make this line? Our favorite construction that tells us that G, E, C, and F lie on a perpendicular bisector of line segment AB. All right, not really related to what we're doing right now, but pretty interesting, interesting process. All right, that's it for Are You Ready for More?